Welcome to the Picture Language Seminar. We're here September 26th, 2023 in Cambridge, Massachusetts, and we're continuing our hybrid experiment to see if we can have both an in-person and online seminar. We're really pleased today to have Ken Duffy. He's new in the Boston area, came from Ireland to Northeastern University in January of this year, and he's going to give us an introduction to forward error correction and a grand scheme to implement it. So Ken, we're very happy to have you here. I'm looking forward to your talk.
Thank you very much, Arthur. I'm just going to share my screen. So, thank you to Arthur for the invitation to speak. It's a real pleasure to be back here in Harvard. I have probably a few too many slides, so I'm going to skip over a few towards the end, but I put them in just in case we go quickly. If there are any questions, people can feel free to ask as they go along in the room or online, and I'm happy to answer them. I thought I would start with a trip back in time because I was reflecting how long I had known Arthur for. And it was about 20 years ago, almost exactly 20 years ago, that my PhD advisor died, very sadly, still miss him. And a couple of years later, we organized a memorial conference for him. You may recognize a bunch of the plenary speakers, including Arthur there, and Di Evans, who's going to speak, I believe, in this seminar series a little bit later in the year, and a large number of other people, including, unfortunately, the late Chris King and the late Mark York, and the late Kathleen Morowitz, for that matter. But when I was moving to the US, I found the group photo that we took from that meeting, and it included a picture of Arthur. And if you're ever wondering what Arthur looked like 20 years ago, it turns about exact same as Arthur looks today. It's remarkable. So I don't know what elixir of life Arthur has been imbibing, but we all need to find out and start taking it. It really is astounding. You look exactly the same. But and you'll recognize a bunch of other people in that photo if you pause it on the talks on YouTube. So lest I run out of time, I'm going to start with some acknowledgements. All of the work I'm going to talk about today has been done in collaboration with Muriel Medard at MIT. This thing started as a theoretical conception one day when we were walking about 2017, sometime in 2017. And we very quickly took it from just being a theoretical consideration into inventing algorithms. And fairly early on, one of the decisions that we made based on previous experience that Muriel had was that algorithms are kind of funny. Deciding whether they're efficient or not, or how computationally complex they are, can be a challenge if you do it solely by doing accounting. And ultimately, the proof is in the pudding. So we started collaborating a long time ago with Rabia Yazicigil, who's in Boston University, who's an expert in circuits. So what happens is we take the algorithms, and with Rabia, we've converted them into circuits and take them out into chips, and you make a chip. And so if you want to know how efficient your algorithm is, you measure the energy efficiency of the chip. So we have typed out 2 chips for these algorithms, even though we started along, only 6 years ago. The other thing as well is we've done quite a lot of work because we've been supported by a very large number of excellent students and postdocs. One of whom is in the room, Pei Hong at the back. Thanks for coming along, Pei Hong. The work has got a lot of momentum. We've been very fortunate with funding from NSF and SFI and DARPA. And as a result of the volume of activity going on this project, I can't talk about it all. I was also conscious that I'm talking to an audience with mixed backgrounds. So I am going to try and be introductory, but at the cost of not covering everything. So if anything is unclear, people can just ask. Okay. So the context for the work is error correction coding, which is an old subject and evidently a very useful and important one. The idea is that if you have digital data, or any data of any description, but everything in my talk is going to be digital. But if you have digital data, then it can be subject to corruption either when you store it or you communicate it. And the reason why the storage and communication are a little bit different is one type of corruption, which is called hard detection, is sort of Roy here in the front of the room writes a file to a disk, and I go and read it later, And what happens is I see that something's not quite right with the file, but I don't know when the corruption occurred. I don't know when the error in the data occurred. You know, so if you go and read a disk, often the errors are not temporarily aligned with when you go and recognize that there are errors. And the other one is called soft detection. Soft detection is where you have side information that may inform you that an error has occurred. So for example, if I'm speaking in the room and the door at the back bangs or whatever, you can kind of localize that it was that part of my communication was likely to have been flawed because there was a lot of background noise, right? That makes sense. So there's two things, hard and soft detection. And the idea with both is you want to be able to identify that errors have occurred in data and you want to be able to rectify them. And of course, this was the topic of Shannon's beautiful opus from 1948, where it makes the apparent realization, you know, that error detection and correction is possible only if a subset of strings are code words. So if I give you strings of length n bits, if every single one of them had meaning, then if you misread one or I miscommunicate one to you, you would never be able to identify that anything had gone wrong. And so the idea is only a subset of the space can be strings that have meaning. So the idea is that out of 2 to the n possible strings you have of strings of length, binary strings of length n, 2 to the k of them, where k is some number smaller than n, are meaningful code words. And we then say that the code has a rate k over n. So for every n collection of bits I give you in the long run, you get on average k of meaning, right? So the n minus k is the redundancy that I've added. And you can already get a flavor for what Shannon is doing. If every string could have been a code word, then should any perturbation of a code word occur, should a bit be flipped, I would result in another code word and I would not be able to distinguish anything had been gone wrong. If only a small density, for example, of strings of length n were meaningful code words, then if I flipped a bit, most likely than not, I would end up in something that's not a code word. I would recognize that an error had occurred. That's called error detection. And then the next step will be to try and rectify the error, right? So to try and error correct. So Shannon asks the natural question, what's the highest rate? What's the largest density of code words you can have in your code book? And figures out that it depends on a statistic of the corruption. So that is the statistics of the noise in the channel or the likelihood of errors in your storage device that we now call the Shannon entropy. People probably know the history to that von Neumann suggested to Shannon that he call it entropy because of its mathematical similarities to thermodynamic entropy, and also because nobody really understood entropy anyway. So nobody would object to you using the term. I thought I would do a little aside, because again, you know, when you're speaking in a seminar series of an ex-president of the American Math Society, it behooves you to have a little bit of good history. So I'll come back to that. The historical aside is people are perhaps aware that probability as a meaningful subject to be studied by mathematicians in the West, that there are 2 Americans that are very, very important in it becoming a legitimate subject for a mathematician to solely study. One of them is Joseph Doob. The other one, I would argue, is Willy Feller. So Joe Doob and Willy Feller were kind of approximate contemporaries, very different styles of mathematicians, and both hugely important. People may or may not be aware that Joe Doob wrote the mathematical review of Shannon's paper. So Shannon's opus, which is a glorious paper. And at the end of it, in a pre-internet trolling, Doob questions whether the author's mathematical intentions are honorable, which really apparently upset Shannon quite a lot. And to be honest, I'm not really sure why Shannon was too upset in that, you know, there are parts where maybe the mathematical intentions are not that honorable. I heard about this at some stage and I wondered, did Joe do a lot of this? You know, was he apparently even do regretted it later, perhaps because Shannon's paper became so important, and then, you know, he was never forgiven for this. But I went reading other mathematical reviews that Doob wrote, and Doob wrote one for another very important paper in information theory, where at the end of the mathematical review, he comments, following tradition, the detailed epsilontics of the proof of the fundamental theorem are omitted. You know, again, a bit of an L jibe. That's for Payhan's benefit, that's Macmillan's paper. So I thought I wanted to be clear that my intentions in this talk are entirely dishonorable, and the epsilontics will be left to the listener. You know, that's just in keeping with the field, as far as I understand it from Duke. Now, the main reason is I want to cover a reasonable amount of ground. The vast majority of what I'm going to talk about, we can do the detailed epsilontics, but I'm just not going to spend time on them today. And then there will be a bit later on where I'm entirely dishonorable. Okay. So
I hope it's all in your paper.
It's all in the papers, yeah. Yeah, anything that says it's a theorem is a theorem. So coming back to Shannon. So what does Shannon do? He says there's a statistic of the corruption. It kind of tells you how much perturbation you're going to get. You know, I have a string in my code book. The noise is going to perturb it. If the code words are sufficiently sparse, you could imagine, you know, how sparse I need to make them that noise doesn't move me too close to other code words. You can imagine there should be a statistic of that, and the statistic is the Shannon entropy. He also proves in that original paper that you get your best bang for your buck as the string length becomes large. So for people who are kind of mathematically, physically minded, what he's really proving is that as the string becomes very large, there's kind of a phase transition. There's a code rate where if you're below that code rate, so if your strings are not so dense, everything will work out. And if your strings get too dense, nothing will work out. Right? So it's a very beautiful and important paper. And it's super readable. And, you know, the way Shannon proves this is very non-constructive, right? So he says, I'm going to make a code book. I'm going to do so by picking strings uniformly at random. So you can imagine I have 2 to the n possible strings. I'm going to do 2 to the k of them because I've got 2 to the k messages. And I'll just make a subset. And the reality is, you know, if Kaifeng and I share such a code book, if I transmit a code word, he can readily lexicographically look up and see if it's in his code book and check. But if it's there, and if it's not, there's a question of how does he decide what the nearest thing in the code book is that he should decode to. That has 2 problems. Like, one of them is the massive storage of this very large code book. And the other one is the algorithmic question of how do you find the nearest code word if what you've received is not a code word. The first of those 2 problems was already solved back in the 60s. So if you want to think of that Shannon's original random code book as being like a language with no grammar, you know, there's no rules to it. He's just picked a load of words randomly in the code, you know, random strings, and said they're the ones that have meaning. In practice, what everybody does for the identification of and correction of errors is you define a mathematically perfect grammar in the following way. You basically define a matrix, so you take your k bits, you multiply it by this matrix that expands it to n bits. It's like a mathematically perfect grammar. You get the idea that now if I want to check if something is a code word, I merely have to take, I merely have to do a matrix multiplication, right? So, and then the fundamental idea is, unlike Shannon's original thing where I have to give you this huge unstructured things, it's sufficient for me to give you the mathematical rules of the grammar in the form of this matrix interpreted in a finite field, usually in binary. Is that reasonably clear? Okay. There's a flying, so yeah, so these linear codes are like a mathematically perfect grammar. And you know, again, if I have a language with a mathematically perfect grammar, I don't actually have to tell you every single word that you can construct. I merely need to tell you the rules of how words are constructed, and you can do the rest. But the next fly in the ointment comes in 1978 when Berlekamp and McAleese and Van Tilburg, they proved that optimal decoding of linear codes is NP complete. So what does that mean? So what they proved was that if you give me a grammar and I receive a string and it's not in the code book, and I want to find the thing that's the best guess to what it was originally before it was corrupted, what they prove is that as the codes become longer and longer, there exists a sequence of grammars for which that problem, the identifying the nearest codebook element, that complexity of that identification scales exponentially. So there exists a sequence of codebooks for which it's it's exponentially complicated in the length to decode, right? That's the NP-ness. The completeness is that actually testing if something is a code word or not is still trivial, right? So if I could give you a guess, if I could say, well, is this in the code book? You just go, well, does the grammar work out? That's a matrix multiplication. I can do that. The problem is if I give you something that's not in the code book, how do I identify my best guess of the thing in the code book that it should have been? Sorry, Roy, you're my bellwether, so I'm going to look at you to see if this makes sense. So what has that resulted in, right? So we've got two things. We've got Shannon saying, get your best bang for your buck when your codes are long. We've resolved the storage problem by saying we're going to use perfect mathematical grammar. And then we have someone coming along going, but you're not going to be able to develop an algorithm that can do decoding, good decoding of an arbitrary code, because some of them it's going to be very complicated for you to do. So the end practical result of that is that the current paradigm, which is people co-design the restricted code, right? So it's like co-designing your grammar, putting restrictions on your encoding matrices such that you have an efficient decoder with them. So it's restricting your collection of perfect grammars so that you have a rule for how you can do the identification of objects, the projection of objects into your codebook if they're not in the codebook. Right? And it means, for example, we have codes everywhere, by the way, like absolutely every device you do is using error correction coding at nearly every layer all the time. We have things like CRC codes, which are only used for error detection. They're very nice grammars, but what happens is, as I said, if I say, is that you receive something, you can say, well, is it in my codebook? You can check that readily. But if it's not in your codebook, you have no efficient means of identifying what it was. We have some codes for which there are very efficient hard detection decoders. So that storage problem where you read something, you go, it's not in my codebook, but I have no side information. I have an efficient algorithm that says, well, given that little information, I can identify my best guess in my codebook. And then we have some codes that are have been developed over the years where there's an efficient soft detection decoder. So where you have the side information and you can determine what was in the codebook. But of course, the practical consequence of this is problematic in loads of ways. Each different code has a different decoding algorithm. It also means that if you and I are agreeing to speak and you need a different decoding algorithm, we're going to have to agree that in advance, and it requires standardization. And so just for example, in your phone doing 5G communications, there are two types of codes. One that was invented in MIT in the 1960s and was repeatedly rediscovered until it was computationally feasible to decode it. And another one that was invented by a student of the person who invented LDPCs in the 2010s. But it means that your colleagues who are in applied algebra have a field day because they're trying to generate structured languages that are super elegant, that have efficient decoders. And so that's what you find going on in the applied algebra field. So guessing random additive noise decoding, which is what I want to tell you about today. How does that differ? The thing about GRAND is that GRAND can replace all of your big puddles of chips where you need a different decoding algorithm for different codes and replace them with a single chip. That's actually a photo of our first chip that we taped out, by the way. And regardless of the code structure, regardless of whether it previously had any decoder or whether it only had a hard detection decoder or a soft detection decoder, we're in principle capable of decoding any of them. We're even capable of decoding nonlinear codes. This first chip we taped out as with the second one we have, has a facility where you can load the grammar onto the chip and it will decode in that language. Now, at this stage, you may be questioning the nature of my honorable intentions. You may be remembering this very beautiful episode of The Simpsons where Lisa makes a perpetual motion machine and Homer declares that in this house we obey the laws of thermodynamics. Well, of course, I'm somewhat constrained in that I have to obey the laws of Shannon, Berlekamp, McAleese, and Silver, right? So obviously there must be some sort of flaw in the ointment. There's a minor flaw in the ointment, which is that for practical purposes, it's not that we can decode absolutely any code. We can decode a code of any structure so long as it doesn't have too much redundancy. So it turns out, and I will give you the back of envelope rather than epsilontic's argument for why, it will turn out the algorithm that I'm going to introduce you to, which will be very easy to understand, can decode any code so long as it doesn't have too much redundancy. It's not a function of directly of how long the code is, not a function of the code rate, which a lot of other algorithms are. It's just a function of how much redundancy there is. So as long as there's not too much redundancy in the code, then it'll happily decode any of them. Okay. So the fundamental idea behind GRAND is actually really very straightforward and easy to understand. So if I transmit a code word to Arthur and it gets perturbed by noise in the environment in that communication, and Arthur decodes very cleverly and identifies what it was that I wanted to communicate, he'd have actually identified two things. He'd have identified the binary string that I sent him, but he would have, as a side effect, he would have identified which bits in the communication were flipped, right? So he's managed to identify both what was transmitted, but also where the corruption occurred in the communication. And the way all of the existing decoding algorithms work is they try and use the structure of the code book to identify and to guess what it was that was sent. And what GRAND does is it does the reverse. It says, if I can identify what bits have been perturbed, then I can identify what code word was transmitted. So you get it? So for decoding to be successful, you have to identify both. You have to identify what was communicated, and you also have to identify what part of the communication suffered corruption. So we go looking for the corruption so we go looking for which bits have been flipped rather than going and looking for the code word directly. So how would you do that? Writing it as pseudocode, the idea is very simple. All you have to do is give me a device that allows me to test, is a string in the code book. As I said, for any linear code, that's just a case of a matrix multiplication. And what I do is, if I can identify, if I can produce noise corruption sequences from most likely to least likely, so the most likely thing will always be the original bits that you receive are correct. So that corresponds to no bits being corrupt. The next most likely thing would usually be that your least reliable bit was flipped, and so on. If you can create those sequences in order, then what the algorithm does is it removes the effect of those putative noise effects from your received signal and queries if what remains is in the code. And it keeps doing so until it identifies something in the codebook. And you can prove properties that this is what's called the maximum likelihood decoding algorithm. It's in some sense completely optimal. And the difference between it and the standard approach is that we're leveraging structure we know about the noise rather than leveraging structure we know about the codebook. It's a very simple idea, but it's also evident that it can decode any codebook. We'll see in a minute that the complexity of the algorithm is a function of how noisy the situation is and how much redundancy you have in the code. And the last thing, which is kind of, was very evident to us, but we didn't think would be very evident to other people, will be it's highly parallelizable. You can do these codebook queries. I can take a load of putative noise effects and query them simultaneously. So I can ask about 10 or 16 or 24 strings and say, are any of these in the codebook? And I can do that in parallel. And that parallelism is very useful because it reduces latency. So originally when we started designing chips to implement these things, we didn't realize that the circuits community themselves would also identify that. So as well as our taped out chips, there are other people in the circuit communities who have published circuit designs for our algorithms. Let me tell you something really obvious and apparent, the simplest piece of mathematics. So if I can sequentially produce noise effects from most likely to least likely, then the algorithm I've just described is what's called maximum likelihood, right? So the idea is that what you receive is what was put in, plus the reason why I'm putting an O plus is likely to be a sum in F2 in the binary field with two elements. A maximum likelihood decoding is if the code words in your code books are equally likely to be transmitted, then the best decoding you can do is to take each and every single thing in your code book and say, given what I received, what's the likelihood that I sent that code word? Given I received this, what's the likelihood I sent the next code word? And if you look through them all and you pick the one that had the highest likelihood, that will be your provably optimal best decoding opportunity. The reason why you can't do that is you want your code book to be large, it has a lot of elements, and therefore that's a very expensive operation. So this is something you can prove mathematics about, but nobody's going to try in practice. What happens with the sequential guessing is because of the invertibility of addition, that if I take noise effect sequences from most likely to least likely and I subtract them from what I receive, the first time that I hit something that's in my code book will also correspond to the noise effect that has the maximum likelihood. I'm going to query through, and the first thing that I find that gives me something that's in the code book is the thing that is the most likely noise effect. So it's a different way of searching for it. So one already knows that maximum likelihood decoding, maximum likelihood decoding is optimal for uniform sources. So you would automatically get loads of results that are already in existence, but actually it gives you a different way of thinking. And the different way of thinking allows you to prove some new theorems, old theorems, new theorems, and actually inspires a bunch of new results. To aid intuition, and the epsilontics can be read in the papers, but to aid intuition, I want to first explain, let me tell you how you should think about this. The way you should think about the decoding algorithm is that I receive something off the channel. I query, is it in the code book? If it is, it's almost certainly going to be my best guess at what the answer is. And if not, I'm going to say, well, maybe the noise flipped one of the bits. If I unflip the bit, do I get something that's in my code book? And you're going to go through that process. And that process has two different outcomes, right? One is I could process noise effect, putative noise effects, and eventually identify the true one that occurred. That will return me to a code word. So that will be the good outcome. I would make a number of queries until I find the actual noise effect that occurs on the channel. And the alternative is I could hit something else in the code book, not the thing that was transmitted. I could merely take something where I received the signal, and I could say, well, if I flip these bits, do I get a code word? And indeed I do, but it's not the code word that was transmitted. So I have these kind of two competing processes going on as I make queries. So let's talk about the second of those first, the one that results in how many queries would I have to make to get a wrong answer. And in order to do this, we're going to go a little theoretical physics. So we're just gonna you're gonna allow me all sorts of slop, and we're just going to think about it to do a back of envelope calculation that you can readily make rigorous. Shannon's original design would have had us make a uniform at random code book. We have 2 to the n possibilities, 2 to the k of which are actually meaningful strings, and because they're randomly assorted and uniformly assorted, if I make random queries to the code book, there's a chance that's about 2 to the k divided by 2 to the n that I would find something that is a code word, right? It's just the density of objects in the code book. Forgetting the -1, because who cares, because n and k will be large enough that it doesn't really matter. So if I repeatedly query my code book The number of queries until I get a correct answer will be geometrically distributed. Get an incorrect answer, find something in the code book that wasn't transmitted, will be geometrically distributed with that probability, right? So it means that, I'll show the picture in a second. It means the expected number of queries until you get something wrong is going to be about 2 to the n minus k, right? It's just a geometric distribution. Every time I make a query to the code book, I run a risk of hitting something in error. That's just a geometric thing. Sure, it's shrinking a little bit because I won't ask the same query twice. The space is quite large, it doesn't really matter. And in the limits, all these things go away. But even if you take super beautiful structured codes, so not Shannon's original random things, even linear codes are designed to try and be as random as possible in some sense. And if you take codes, and in this case, the blue line or the black line is that geometric distribution. So it's just a geometric distribution with a probability of 2 to the k minus n of getting a correct answer. And if you do a load of different simulations with different codes of different sizes and different lengths, but all of whom have the same number of redundant bits, n minus k, and you query how many queries do they have to make till they get a wrong answer, you'll find that it fits very well. It's sort of a universal phenomenon. So the number of queries you make until you get a wrong answer is really very easy to understand. The thing that's difficult is how many queries do you need to make to get the right answer. And the study of that as a topic, that's a topic called guesswork, goes back to at least 1994. So there's a guy called Jim Massey, who's no longer with us either, unfortunately. And Jim, I can facetiously tell you in a one-page paper, the reason why it's facetious is that in this conference at that time, all papers were one-page papers, so it doesn't distinguish his paper. But Jim asks the following question in that paper. If you take, I give you a discrete distribution, right? So a distribution actually on a finite set, and you know what the probabilities are of each object in the finite set. And I ask you, so you know the set, you know the probabilities, and I'm going to let you ask me yes/no questions. I'm going to pick one of those values from that distribution, and I'm going to let you ask me yes/no questions. You're going to say, did you pick answer 1? Did you pick answer 2? Did you pick answer 3? You're going to ask the question, well, that is called guesswork. How many queries you have to identify, yes/no questions you have to ask until you identify a randomly selected object. That's called guesswork. And what Jim asked was, does the average amount of querying you have to make to identify a randomly selected object, does that bear any relationship to Shannon entropy? That was his question. Make sense? So, okay. Obviously, the optimal strategy, knowing nothing else, is if you know the probabilities with which all the objects are selected, you should ask the most likely thing first, second most likely thing second, third most likely thing. You can prove that that strategy is stochastically dominated by every other strategy. So in every mathematical sense, it's as good as it gets. And Jim's paper basically answers the question in the negative. It says that Shannon entropy is not the right metric for this process. And the toy example that one has in one mind for why this is true is if I give you a random variable that looks like this. So this is its discrete distribution. Most of the probability is on a single value, but then the rest of the probability is shared amongst the other ones. The Shannon entropy of this random variable will turn out to be quite small because so much of the mass is on a single outcome. But actually the average amount of guessing you have to do is pretty bad. Most of the time you get it right on your first query because there's like a 50% chance it's number 1. But if it wasn't number 1, it's now uniform. It could be anywhere in there. You're just breaking ties equally likely. And so conditioned on the first one not being right, the average is going to be halfway down that list, right? And so it turns out if you go and try and do the bounds, you get like the lower bound that's in terms of Shannon entropy, but there's no neat upper bound. One-page paper, very pretty. People I know because there's quantum information theorists in the room, there are people in quantum information theory who've done some work to try and extend guesswork considerations into quantum information theory setting. Erdl Arakan, which deserves greater mention in this talk than I'll have time to describe, but who managed to persist with a problem all the way through the 80s, all the way through the 2000s, and has resulted in technology that's in everybody's phone in this room. So you got to give Erdl props for that. Erdl Arakan in 1996 went back to Shannon, or went back to Massey's problem, and said, okay, Shannon entropy doesn't appear to be the correct metric. He wanted to study it again, but he has to put some structure in the problem in order to make it mathematically analyzable. I can't just really just give you a single arbitrary random variable and ask you to give me a generic bound. You can't get any further really with it. So what does Erdl do? He says, imagine I give you a string of length n made up of independent and identically distributed characters. And what you're going to do is we're going to play the exact same game as before. For a string of length n, you're going to pick a random string from a distribution that I know, and I'm going to query until I find your string. I'm going to query from most likely to least likely. And how hard is that guessing problem, and how much worse does it get as the strings get longer and longer? You expect it to grow exponentially. The number of potential outcomes is growing exponentially as the strings get longer. I won't overly dwell on this, or we won't get it to the later results, I guess. Get it run out of time. What Erdl ended up proving was that he looked at the moments of this guesswork. So you're looking for, like, if alpha is the one, it's the mean. How does the mean of the guesswork scale? If you put alpha equals 1 into this formula, you get what's called Riemann entropy with parameter 1/2. So the average amount of querying scales with Riemann entropy and parameter 1/2 rather than with Shannon entropy. It's necessarily worse. It's actually really quite easy to understand, to be honest, from the other picture. The reason why it's worse, and the reason why there's a bit of a conundrum, is that with high likelihood, you will get the right answer within something that's dominated by Shannon entropy. But on average, you end up having to do a lot more querying because your early queries have lots of merit and value and high probability. But if they turn out to not be right, you have to make more and more queries. Anyway, his results were extended. His original things were IID. They've been extended to Markov chains. They then got it extended to suffix shifts there. It's a hugely generic result. And with a student a long time ago for fun, we managed to convert all these results on scaling behavior of moments of a distribution and convert them into large deviation behavior so that we had estimates on probability distributions. And so one can try and address that question I asked previously, where I have a number of queries until I get a wrong answer, number of queries until I get a right answer, and I can just consider those two processes as competing. And I can do an analysis of that where it recovers pretty much all of the known results in Shannon theory part of coding. So you can go and do the math very nicely, and you can figure out properties of the likelihood of error, properties of the complexity of the algorithm, and you can get a load of theorems. And they are the content, which I'm not going to describe because I'm going to invite you, if you're sufficiently interested, you can go and read it. They're the content of the first paper that we wrote on Grand, which was purely mathematical in nature, that said if you executed this algorithm, then what would happen would be it would evidently recover all the results that people previously knew, and then it gave us a bunch of additional ones, including things about what happens when your code book is above the code rate, as above the channel capacity. So it's in some sense, it's mathematically very natural. It looks like it was sitting there waiting to be found. But what I wanted to talk, and I guess I probably have about 10 or 15 minutes, is that right? Right, yeah, okay. What I really wanted to talk on, and I've been going a bit slow, is what happens with soft detection. Those previous results I described to you is that you have a distribution for a random variable, you know, a priori, and you produce this rank order querying. The thing that people are most interested in, the stuff that all your phones do, the stuff that your Wi-Fi cards do, is they all use this side information called soft information. So when you received signals, as well as me telling you this bit is a 0 and this is a 1 and this is a 1, I also give you a confidence measure in the likelihood, you know, how firm is my belief that it really is a 0 or a 1. That soft information, which is you know, side information to help you inform your correction, it's typically, you can imagine, it's harder to incorporate into your algorithms and harder to use, but it gives you a massive gain in error correction performance, because rather than blindly searching for an error, if you know that it's likely to be localized in a certain part of the communication, you can focus on it and correct there. So soft detection algorithms are really what people super care about. And so fairly early on, we started trying to develop variants of that previous technique, but that incorporates soft information. And the crucial thing to do so is in an algorithmic way that is efficient and realizable. Let me give you, oh yeah, I won't get to explain this in full, but maybe it'll be a topic of conversation for another time. If you go and read any paper on error correction, you will see that they assume every bit is flipped independently. And you might query, well, that doesn't seem very realistic if I'm talking and a door opens or shuts. There's a localization in the interference that would make the noise be clumped, you know, the corruption be clumped. Because everybody else's decoder is searching in the code books for the code words, their decoding algorithms assume every bit has been flipped independently. And because this is engineering and not science, you can convert reality into the reality that you would like. So the way that's done is something called interleaving. So what happens is, if Roy has a bunch of bits he wishes to send me, actually what happens is they're contiguous in meaning for Roy. He will send one bit, leave a big gap, send another bit, leave another big gap. You basically leave a long decoherence time between each bit that he communicates, and then I reassemble them at the far end and I decode. Thing I'll run out of time, I won't get to speak about, is interleaving is bad for kind of two reasons. One that people would know is it induces latency. So Roy has to slow down his communication to me because he has to artificially delay the bits. But also, information theory tells you are throwing away performance. You can imagine if the original noise on the channel was correlated and errors were clumped, they should be easier to find than if you take them and they're clumped and you sprinkle and distribute them. So the reason why we do that is just everybody's existing decoders assumes it's true, and so we twist the engineering to make it so. But as a result, it means that any paper you read, if it's soft detection, it will essentially typically assume that the channel is what's called additive white Gaussian noise. So what do? I have a 0 or a 1 I want to send you. If I send you a 0, I actually send you the number +1, and that's subject to Gaussian noise. If I want to send you the number +1, I send you the number -1. And I'm subject to Gaussian noise. And what you receive is that symbol. If it's above 0, you decode it to be the +1 symbol, which corresponds to 0. And if it's below 0, you say that it was most likely what was sent was -1, which you decode to +1. So it's, basically, I have two symbols and I send you them, and they're perturbed by additive white Gaussian noise, and I can treat every bit as if it was independently perturbed. From a mathematical point of view, you can think of it a slightly different way, which might be easier. Every bit that I send you, I can give you a posterior probability that it was flipped. So I can say, I think this was a 0, but there's like a 10% chance that it was wrong. Or I can give you this 0, and there was like 50%, a near 50% chance that I was wrong. I was very unsure of it. People use this information to try and improve their decoding. So what do we do in grand. In that previous example, this is like I've got 500 bits. Each bit has been independently affected by noise. And so my posterior beliefs on each of the bits are scattered all over the place. There's no structure in it. If, however, you were to rank order that previous picture from most likely to least likely, you get something where structure starts falling out. It's merely because you're now estimating a cumulative distribution function on its side. Like, so if I give you a bunch of independent observations from a random variable and I rank order them, which is called order statistics, it's very like estimating a CDF. And what happens is each individual bit is all over the place, but when I rank order them, if I take repeated samples, you get something very consistent. In the comms world, people don't like thinking of the posterior likelihood that a bit is flipped. Instead, they give you the exact same piece of information as what's called a reliability, which is an absolute log likelihood of the likelihood that a bit is flipped versus that it's not being flipped. That's what they prefer. So if you were to rank order these things by reliabilities, this is just a different measure of how trustworthy each bit is, and you plot them, you'll get something that looks like this, okay? So if you're in a noisy channel, this has nothing to do with the decoding algorithm, nothing to do with anything like that. It's just the way comms works. If I communicate something to you, it's a pretty noisy channel. Then if you rank order the likelihoods, the LLRs that you receive, you get something that looks like that. And in a past life, I was running a very large doctoral training center in data science, and I hired a bunch of very good statisticians. And in the early days, I had a lot of confusion with them because my sensibility of what a model is has been informed by physics to a great extent, and that I expect you to give me microscopic descriptions that I expand to macroscopic ones. But if you're a statistician, a lot of models are phenomenological. They look at this, and rather than tell me why this is coming about, which is something that you can do, they look at it and go, that's a line. So if you put your statistical modeling hat on, you go, that's a line. And if it's a line, something absolutely beautiful and magic occurs. So because it's a line, talking in probabilities, if I'm going to give you a binary string, and I'm going to tell you for each bit in that binary string, I'm going to tell you there's a probability that I think it's wrong. And if I want to know what's the probability that certain bits are flipped, well, it's the product over all the probabilities that none of the bits are flipped. And then well, I do want to flip bits. I just want to swap out a flipped bit for a non-flipped one, right? So the likelihood of any sequence, this is just the Bernoulli sequences with probabilities pi. And if you rewrite that in terms of our log likelihood ratios, it turns out the likelihood of a noise effect sequence, the likelihood that bits are flipped, turns out to be just related to the sum of the log likelihood ratios at the bits where you want to flip them. So remember, I want to produce these noise effect sequences from most likely to least likely. And if these LLRs happen to be aligned with some slope where I don't care about what the slope is, it turns out that I don't need to know the slope to know that noise effect sequences, in order to rank order them from most likely to least likely, it's sufficient for you to rank order the bits, tell me this is the least reliable bit, this is the second least reliable, and so on. And the likelihood of a sequence turns out to just be the sum of the bit position where I'm going to flip, the sum of all of the bit positions where I'm going to flip. And I explained this too fast. Let me try one more time. If I tell you I'm going to give you a Bernoulli string and every bit is flipped equally likely with a probability that's less than a half. In order to produce for me strings from that distribution from most likely to least likely, you don't actually need to know what the bit flip probability is. If the probability is less than a half, the most likely thing is that nothing was flipped. The next most likely thing is that one bit was flipped, and it could be any of them. the next most likely thing after you've done all them is that 2 bits have been flipped and so on. What happens when you have soft information? And if these bit flip probabilities are no longer the same for every bit, but are following a line, then it turns out that the equivalent metric, as opposed to counting how many bits are flipped, is you count, you add up the location where the bit is flipped, which we call logistic words. Why does this matter? The reason why it matters is we want to use the soft information to help us decode, but we don't want to really use the detail of it. So what we do is we say, okay, every bit you receive has a different probability that it was flipped, but all I need you to do is to give me a rank ordering, tell me which was the one you trusted the least, which was the one you trusted the second least, which was the one you trusted the third least, and so on. And if you tell me that permutation of those bits, that's sufficient for me to proceed and decode, because once I have that permutation, I can readily construct sequences of bit flips from most likely to least likely. Something very pretty happens here too. This thing turns out to be a problem in discrete maths and constructive combinatorics called an integer partition problem. And it turns out that you can make very, very efficient algorithms to solve it. So it means we can take soft information and decode readily with it. I'm going to skip over this. I just want to show a couple of performance pictures. The purpose of that stuff was merely to say that we implemented this algorithms very in collaboration with Rabia and put it into a chip, and it was published earlier this year, and it's the most energy efficient decoder ever published. But let me tell you a couple of mathish things and then just to end. The way people assess the performance of decoding algorithms is the following. On the y-axis, what we have is the block error rate. So this is the fraction of decodings that are incorrect. And what we have on the x-axis is a measure of how much noise there is in the system. As we move further right, there's less noise. It's the signal to noise ratio. As we move left, there's more noise. So as the channel gets noisier, you might expect that I make more errors. And as the channel gets less noisy, you should imagine with a fixed code, I will get better performance. The dotted black line at the top is what would happen if you use no code. So if I send you n bits, what's the likelihood that even one of them is wrong? Because even if one of them is wrong, your decoding will be wrong. So what does coding give you? What coding gives you is this massive improvement in performance, massive reduction in how many decodings you get incorrect. So in this case, we're taking, for every 128 bits I send you, 112 of them have meaning, and 16 of them are there to help me correct errors. And what you see is that I get a multi-dB gain in performance. It's why we use coding everywhere. There's results from a math result from the 1990s that tells you if you picked a code at random, it's likely to be good. But the thing is, people couldn't decode them. Normally you can only decode specific codes. And what this plot is showing you is the error correction performance of 4 very different codes, one of which is even non-linear. It's using AES, the encryption function, to try and make a code book, just as a demonstration. And it's showing you that even though we do all this work to try and make very specific codes, this math result, now that we can realize it in practice, is correct. Every code is nearly equal. I will say, as a slight aside, and I have 1 minute, that when we started this project, we had this idea that we would code mine. We had this universal decoder, so we would go off and try and find really brilliant codes. And then we discovered that even if we picked a code at random, it was really good. And in fact, the only systematic codes, well-known codes that we found are bad, are incredibly celebrated ones that are actually in your technology. It turns out it's very hard to make a bad code, but actually polar codes are it. Anyway, I'm going to skip this and merely go to this final bit. So I wanted to try and introduce forward error correction to you. It's used absolutely everywhere. I wanted to try and introduce the idea behind guessing random additive noise decoding. So we've got a very large team doing an awful lot of work on it. So we've already translated these things into hardware, both with hard detection and soft detection, both published in very good places. The algorithms are inherently highly parallelizable, so they're low latency. But there's all sorts of additional things these algorithms have that I think stems from largely from the math, in that when you go about tackling this problem by considering it through the lens of guesswork, it turns out to be quite natural, and so stuff is revealed. So one of the things which I didn't mention today is that every time I give you a decoding with this algorithm, in addition, it can give you an accurate likelihood that the decoding is correct. And part of the reason, part of the reason that that's very important is, of course, if the coding is not correct, you should discard it. I didn't get to show you, but using ideas that are actually stolen from thermodynamic probability theory, we've actually been able to produce a version of this that can decode in correlated noise, which is universal, and it outperforms. So what happens is people normally avoid correlated noise because it makes their performance degrade. In our case, correlated noise is more structured, and therefore we decode better. And so we keep a web page on MIT that has a collection of all of the papers in the tutorial and all sorts of other things if people are interested. And this work really does stem from theory through the design of algorithms to actual implementations, and in all parts of that work, there's still stuff to be done, including with rigorous epsilontics. So I'll close merely by leaving a slide up to say that the Northeastern math department will be hiring. The advert will be up very soon in quantum information science. There's going to be a 10-year track or a 10-year open rank professorship. So if anybody is interested, please have a look at the website and a little bit. But at this stage, I would like to thank you for your attention, and I'm happy to answer questions if there are any.
Well, thank you very much. That was a beautiful overview of a new subject, and it's really interesting.
Thanks.
You alluded to the fact that there's some work on quantum guesswork. And is there a quantum grant?
There are 2 quantum grants, at least. So there's at least 2 groups in Europe who've taken grant and tried to use it for quantum error correction. And actually, people in the US have been trying to drag us into it too. So, I'm insufficiently familiar with the problem area to appreciate how different it is. I do know from an experimental group actually reached out to us, and the reason they wanted to talk to us is one of the things is in quantum communication at the moment you have a smaller number of bits, or you have smaller amounts of data for some reason that people are sending, but also Grand is able to use characteristics of the channel, whereas to improve its performance. So if people can well characterize quantum channels, maybe we will be able to outperform traditional techniques.
Are there some questions in the room here? Yes, Kai-Feng.
So does your result depends on the type of noise?
The mathematical results, the original mathematical results, assume you have additive independent noise, but beyond that, no. And in fact, the gap between the mathematics and the practice is really how do you make, if you knew statistics of your noise, how do you algorithmically generate noise effects from least likely to most likely? But actually the math is incredibly robust. So the math says as long as you can do that, everything is going to be perfect.
And also in the mathematical theory, theorem of the guesswork,
Louder.
You are considering the asymptotic version, like it's equivalent to some linear entropy or infinite entropy. So what's the result about the one shot version? Like we only guess one time. Is it lower bounded or up bounded by some, still bound by this kind of linear entropy, like mean relative to the linear entropy of max linear?
Right. So if things are IID, there are upper and lower bounds that have terms in them, and there's even, yeah, the lower bounds are, and actually there's a large production of people refining those bounds, but you don't get anything as elegant as when you go to the large N regime. But actually, it's a pretty harsh asymptotic in the sense that you can see it's you're pulling out a dominant exponent, and the prefactors may be enormous, and in fact, they really are likely to be, because people have, for example, proved, which makes sense in the asymptotes that you consider here. In any practical circumstance, I should query from most likely to least likely, but in those asymptotes, I can actually query at random and get the same performance. So, you know, I rather than doing some very logical thing, I could query at random with likelihoods from your distribution, and you'll get the same asymptotic performance. So the asymptote is quite weak. People produce both sorts of results, and actually on quantum guesswork, people are producing both sorts of results too. Yeah, even in the classical world, people are interested in still in guesswork for single distributions, because it informs you about things like how hard is it to hack a password, because you have a distribution of passwords and it's a single distribution rather than a large N limit.
Yeah, and also like for the guesswork, you're considering the discrete probability distribution, right?
That's right.
So how about like continuous version? Because the differential entropy, like for the alpha equal to one case is like 1/2 linear entropy, but I think it's not well defined for.
It's not well defined for continuous processes.
Yeah.
I don't know much about. I'm not familiar with results on continuous guesswork. There are some, but I don't fully understand the framing of the problem. For everything that we do, we have only cared about discrete things, because even though the perturbation of your signal is continuous, in the end, all I really care about is what bits has it flipped. And so we have a discrete thing. So there are results in guesswork in the continuous case, but you'd have to go read the detail. Yeah, but I do think they do have. I do think that they've actually, I think, been trying to generalize Rini entropies in order to describe those processes.
So there are other questions here? Or are there online questions?
Another question.
Let's see if there are any online questions. I guess, yes, go ahead, Kai.
So what's it? So although you are using the like discrete probability distribution, discrete variable, but your noise is like a Gaussian. So what's the difference between the Gaussian and the like they use the bit flip, like the knowledge?
Yeah. So so what happens is, of course, my original data is digital and my final data is digital. In between, I take my bits and I modulate them to a continuous signal, and that's why they're continuously impacted. At the end, we're only interested in what bits were flipped. But say, for example, in the most basic forms of modulation, you can relate the signal to noise ratio, so the variance of the Gaussian, you can relate that to the likelihood that a bit is flipped. Mm-hmm. So the two are related. What the continuous thing gives you is posterior beliefs, really. It allows you not just to say that the thing is a 0 or a 1, but that you have a certain level of belief in it.
But it's my understanding, right? Like although it's Gaussian and variable, but you need to decide like if the initial input is +1 - 1. After the Gaussian random variable, you may get any like a real number, and you use it less than 0 or larger than 0 to decide it's +1 - 1. But it is still somehow like you have the bit. It's somehow equivalent to the bit flip, like
it is. But what happens is, so an additive white Gaussian noise channel, if you get no side information, looks like a binary symmetric channel. Yeah. The reason why it doesn't is, imagine I give you, I'm sending +1 or -1. if the Gaussian noise moves me much further up, I'm very, very sure it was +1.
Yeah.
Whereas if what I receive is down near the boundary where it's 0, I'm uncertain. So as well as giving you my demodulated belief, so that's my best guess as to whether it's a 0 or 1, I can also calculate, and this is what every piece of equipment in this room is doing, I can calculate a likelihood that that bit is wrong and try and help use that to inform, you know, because if what I get off the channel is in the code book, then that's definitely going to be what I think is right. But if it's not in the code book, I should really look at the parts of the ones where I was uncertain of those bits, That the reality is actually a bit more complicated because I don't send you one bit at a time. I don't send you that thing is called binary phase shift keying, so you can use that, but it's not usually. Normally I send you a wave, and in the wave it contains a number of bits that's larger. So really we draw points on the complex plane, and each point in the complex plane, it'll be a grid, and each point will correspond to a different number of bits. So there's a lot more complications going on in the background that often coding people get to ignore because of the interleaving that I mentioned.
So there are other people here who've studied air correction. Do you have any comment?
I'm curious about if this method also works for quantum code. So in quantum code, there is a lot of degeneracy. So even though an error is not 0, but it cannot create a logical error.
So yeah, Arthur was asking similar questions. I don't know enough about quantum to be sure. What I do know is that at least 2 teams reached out to us after they read Grand and have since written papers on quantum error correction. One of them, we had a paper with Pei Hong where we were going to call an algorithm Q Grand, and we very generously allowed a quantum group to take Q Grand instead because they wanted to do quantum error correction. And we wanted Q for quantized. We could think of something else for quantized. For quantum, you can't think of anything else. So Elias Hanzo, there's a guy in Southampton, so his team have a paper, and then I think there's people in Spain, but I'm insufficiently expert. I need one of you guys to explain to me what a quantum error correcting code looks like. In fact, that's something I'd enjoy very much if you could.
So we're going to get together again.
We will. I'll need that. That'd be great.
Are there any other comments or questions?
If not, I'll get across town and teach my class.
Well, thank you again, Ken, for a very beautiful talk, and I think this is going to lead to a new collaboration. Thank you.
Thanks, everybody.
See you next week.